Thanks for joining today's webinar. I am Jorge Rodriguez, a hardware engineer at Power Smart Control. Today, I'm going to introduce you with a demo our new development, which is a SmartRCP or a Smart Rapid Control Prototyping Platform. I'm going to share my screen now to continue with the slides. So, yes, I share my screen. You should be seeing it now.
Yeah.
Perfect. So what are we going to do today? So the challenge is to use the rapid control prototyping system, our SmartRCP, in order to develop and validate a control algorithm in real time. So what we are going to do is to control a small buck converter, which is a demo board we supply with the product, this board in here, with the SmartRCP. As a result, you will see the systematization and how the workflow is performed in order to deal with SmartRCP tools. So we provide a template with the product. We will cover how to use that template and how to perform the full control. But prior to that, we are going to check exactly how we are going to proceed. We are going to use a silence workflow tool. So we are going to use Vivado and VTIS HLS for high-level synthesis. Also, we are going to use VITIS in order to program the PS part of the system on chip embedded in our SmartRCP platform. We are going to do that with the help of several templates we provide. Today, we are going to review one of the templates, but there are several other more. So afterward, we will check VITIS, which is used to program the PH part. Then we are going to perform all hardware connection of that demo board, the buck converter demo board, with our SmartRCP system. Then we are going to connect the full system, command that with a console we provide, and check all the real-time waveforms in an external oscilloscope, but also in an embedded oscilloscope that we provide. So what are we going to learn today? So basically, how to use a SmartRCP. The main goal today is to get introduced in the workflow and the capabilities of a SmartRCP system. So we will start with Vivado. We will perform an IP review. So taking the VHDL IPs, the high-level synthesis IPs, the AXI IPs, etc. Then we will go to VITIS, and then we will deal with the console and the embedded oscilloscope. So we have seen what we are going to perform today, but what are we going to program today? So this is a simplified control stage of what we are going to embed in the SmartRCP system. We are going to take the demo buck converter board output voltage, which will be something from 0 volts up to 5 volts. We will perform there then in a SmartRCP a low-pass filter in order to clean that voltage. We will perform a gain adjusting. Then we compare that with a reference. Then we will have a PID compensator and then a modulator. The output of this modulator are going to be the pulses required for the main transistor and also for the auxiliary transistor. This is a synchronous buck converter, so there are 2 transistors. Those will be connected to the buck converter. So the low-pass filter is going to implement a moving average filter in order to remove the sensing noise and also the switching noise. Gain adjusting is going to compensate the ADC gain, the analog to digital converter gain, and also the sensing stage embedded in the buck converter demo board. This gain has a factor of 2, so we are going to compensate that as well. Parameters of the PID can be modified in real time with the console we provide. We will see that in a minute. If we take a more detailed view of that, we are going to have these control states. This is what is really into the SmartRCP system. We are going to obtain the buck converter output voltage. We are going to introduce that into some format adapting blocks, and then we are going to use that in we are going to feed our embed oscilloscope with that signal. Also, we are going to perform the moving average filter we said before, the PID. This block make the reference comparison, also implement the compensator itself, and also implement some limiting. Then we go to the digital PWM. In this case, the carrier and also the pulses are connected to the embedded oscilloscope. Then we have a PWM selector in which we can select if we are going to trigger by an open loop pulses or with closed loop pulse. Also, in this case, we are going to sense the back inductor current. By the way, we are just going to send that to the oscilloscope. This signal is not used to control the converter. However, it is proposed for the people interested to close the loop also in current. Okay, so we have checked all we have programmed into the SmartRCP. So let's check exactly what is the buck converter demo board. This is the demo board. You can see it contains both power transistor, some resistor load. Also, we include here a passer to create a load step. In here, we have a USB port, which is the input power for this converter, so 5 volts. In here, we have a Ethernet connector in which we introduce the PWM signals, and those two Molex connectors are for the current sensing and for the output voltage sensing. Here is the PWM transceiver, here is the driver, and there are several test points all over the board. For example, for the PWM, the real ones connected to the power transistor, we have a test point of the output voltage and another one for the current at the inductor, and also several test points for ground, etc. This is the connection we are going to perform today. So we are going to connect the output current to one of the input analog connection port of the SmartRCP platform, the very same with the output voltages. We are going to connect the Ethernet wire in order to send the pulses to the converter, and also in this USB port we are going to connect the typical charger for a mobile phone, etc. This slice combines the hardware with the software. So in this one, we combine the hardware connection with exactly the control states that is performed inside and the data flow. So we are going to sense the output voltages of the converter. This is introduced into ADC G71C port, which is this one. Then it is filtered. It has a PID. Sorry. Then it closes the loop, and that signal is introduced into the PWM selector. Also, we have a collection of open loops PWM pulses, which can be also supplied. Any of them will be sent to the 36A port, which is this one, and will be fed to the power converter. In here, in order to configure the control loops, etc., we are going to include a couple of AXI IPs, which are called parent back 1 and parent back 2. Those two IPs send the parameter from the Cortex A53 processor to the PL part. Also, we are going to use one of the real-time processor embedded in the system on chip included in order to deal with the embedded oscilloscope. This connection is also performed, so we are going to check that in a minute. So, what we are going to do now, I'm going to toggle from the slices to a camera. This is my setup. So, hello. I'm going to connect all the wires and also power the oscilloscope. This is the SmartRCP system to which we have connected an Ethernet wire, a micro USB wire connected with the computer. This is the wire we are going to use to program that, and also a power plug. So I'm going to connect the wires for the feedbacking of the signalings. So this one is for the output voltage. This one is for the inductor current. I'm going to insert the power USB. I'm going to connect now the Ethernet wire for the PWMs. So this one. And now I am going to connect the oscilloscope probes, which will be in the inductor current test point in here, with the ground connected in this test point. Sorry, it jumps. And the very same with the output voltage. So I'm going to connect it here, yes. And the extra ground test point is in here, yes. So more or less in here, you can see we have connected the output voltage wire, the inductor current wire, the PWM wire, this purple one, the power feed wire, and a couple of probes connected to the oscilloscope to check the current across the inductor and the output voltages. Okay, so now that we have seen the hardware part, I'm going to switch to Vivado to show you the template we have created. So I will check here. Sorry. Yes. Vivado. I close the camera. And while Vivado opens, I'm going to show you what we provide. We provide in here a zip file which is called back demo. This includes the micro SD files, just in case you want to directly program the board. We provide the software interface for the oscilloscope, the embedded oscilloscope, and also for the back console. And we provide in here also the project. It has the high-level synthesis IPs, which are the gain and offset adjusting, some format converter, the moving average filter, PID compensator, digital PWM, modulator, etc. We have in here the Vivado project, and in here it is the project for the microprocessors. So I'm going to open this, copy this address, go to Vivado, project, open, and I paste in here. Select the one and open it. Will take just some time. We are almost done, yes. In here, this is the typical appearance of Vivado. We are going to open the block design to check all the IPs we have included. And in here, I'm going to make this window a bit bigger so we can see with more detail. We have several IP blocks. The main one is this IP. This IP is provided by us as a template, and it includes all the configuration of all the hardware included in a SmartRCP system. We can say it is a compendium of all the drivers included in the board. For example, we have here the input data for all PWM channels. In this case, as we are only using one of those Ethernet connection, mostly all of them are synced to a constant. Also, we have all the error lines provided also in the PWM channels, the UART communication, RS485, etc. In here, we also have all the analog to digital data and that we are measuring with the ADCs. We are only using a couple of channels, one for the output voltages of the buck converter and the other one for the inductor current. Yes. We have here the quick and low channels. We have also PWM inputs, the same RS485, etc. All the communication of the hardware of a SmartRCP system is covered with this IP. So we are going to start with this IP and connect more IPs. What more are we going to connect? Obviously, our oscilloscope. It is an 8-proof oscilloscope. We are going to use, as we said, one block in order to modify the gain and the offset of the inductor current. So in here, we introduce the data of the current we get from this driver, you see, from the ADC. This one is connected into the input data. We have these other inputs which came from an AXI IP in order to modify the gain and the offset to compensate that. And the output of that block, I mean the current across the inductor with the gain and the offset modified, is inserted into the oscilloscope at channel 3. We are going to perform the very same with the output voltages. So the output voltage is this signal in here. It is connected into this block. So we have here a format adapter for that voltage. Then we go to the oscilloscope and also in this channel. Then from this data in here, we go to the digital control voltages mode. In here is the data input, which is this one. This one came from the moving average filter, which in turn came from this input. You see, this input is the ADC signal, which is sensing the output voltage. So we go to the moving average filter, then we go to the PID compensator, which whose output goes to the digital PWM modulator. And the output of here are these pulses, which goes with those lines to a PWM selector, which select between open loop pulses or closed loop pulses. You see that closed pulses came from the compensator plus the digital PWM modulator, and the open loop pulses came from this IP. The output of this PWM selector block is connected to this PWM data port. This data port is the one that is going to send the data to our buck converter. So, as you can see, the main blocks are, the main driver block, which is this one. This is the template block. The format adapter for the inductor current. The format adapter for the voltage at the output of the converter. The IP block for the average filter for the PID and for the modulator. The PWM selector. The PWM generator for open loop pulses. And in here we have the embedded oscilloscope. There are several other IPs, for example, the think processing one, the AXI, reset, clocking, etc. But those are the main ones. So also we have included in here an ILA, which is the logic analyzer provided by Vivado, in case users want to check several waveforms as well, because our oscilloscope is completely compatible with the logic analyzer. So I close in here, I open it in here, and in order to speed up the webinar, all the synthesis and the bit stream is fully created. Otherwise, you will have to select in here, create bit stream, and then with file export the hardware, including the bit stream, in order to continue in BITES. So I'm going to switch now to BITES. So we are going to use the BITES Classic, and I'm going, while it starts, to look in here for the folder which include the project. I copy that address, paste in here, and launch. May take also a few moments. Yes. In here we have a small code we have created. This code is quite straightforward. We have a parameter initialization. We have a console, a communication with the console we provide, in which all the parameters that the user provide or update into the console are going to be collected in here, and then to program sent to the FPGA part by means of those drivers. So I'm going now to switch on the SmartRCP system. Yes, it is switched on now. I'm going to open some of the lines we have to use in order to program it. So due to a Vivado issue in this release, we need to manually connect this board because it is based on Crya K26. So we connect that. Yes, we select the target. Yes. Change the register. And we provide a system reset. Yes. So now we are ready to program it. So how are we going to program? We are going to use, 1 second, please. It is opening. Well, actually, it seemed to be not responding. Yes, now. we are going to configure this launcher in order to include the program of the embedded oscilloscope. In order to work the oscilloscope, you need to include in the Cortex 5.0, we need to include the application. So in this case, I have it in here, but you can find quite easily into the back demo project and the in here. Sorry, in the boot files, and here you can see it. You see, and in here we are going to add the program we have just created, the one we are going to debug. So I close that, don't save, and I'm going to launch that. While it sends all the configuration, I am going to open the application. So I'm going to open the back software interface, which is the console, this one. This is the console of this program. We have to select in here the USB communication port that we have. In my case is the COM23. So I click in here. And now I am configuring my power supply in order to power our buck converter. I'm going to click in update. And also I'm going to launch the oscilloscope. To launch the oscilloscope, which is this application, we need to specify the correct IP. To do so, we are going to introduce the IP. This is hardware written into a micro SD card, which is plugged into a SmartRCP system. And in case you do not know what IP we have, we can just remove this console, connect a serial client to COM23 in my case, and it will be written down at boot. So it's 10, 102, 10, and 199. So we update the config. Now we are online. So we close that window. We want to check the output voltage, which is channel 1, and also we are going to look for the inductor current, which is channel 3. So I update the configuration. I click on start, and I'm going to provide here a zoom. Yes, in this case, as you see, we have a switching frequency of 100 kilohertz and a duty cycle of 30%. In this case, we are in open loop, so that provides us an output voltage of 1.5 volts and this current across the inductor. I'm going to switch on also the camera, so you can see here. In here, in blue, this triangular waveform is the inductor current. This yellow flat line is the output voltage. So in here, we have exactly what we are looking out in the embedded oscilloscope. I'm going to change now in here the duty cycle. I'm going to increment that to 70% and click on update. So, well, trigger just get off scale. Sorry. Yes, someplace around in here, we have a stable trigger. And also the output voltage is around 2.5 volts or maybe 3. So you see, we have almost 3.5 volts at the output and the current has increased. We can also change the switching frequency, for example, from, well, let's reduce the data cycle in order to see it better. Let's increase the switching frequency to 300 kilohertz. And you can see here, we have exactly the same. The ripple have reduced, but we still have ripple across the inductor current and also the output voltage. Now I'm going to change to closed loop. So I click on closed loop and update. We have now an output voltage of 2.5 volts. You can see it here, the very same voltage specified in here. Switching frequency is 300 kilohertz, the very same, but it can be changed. And we can also check a lot of more things in our embedded oscilloscope. For example, channel 3 is the inductor current. However, channel 6 is the modulating signal. It is in counts, so it is in 300 and something. But this is the signal we are used in order to modulate our control. This is directly taken from Vivado. This waveform, which is the output voltage, and the waveform we have before, which is the current across the inductor, are signals which are sampled by an ADC and then measured with the embedded oscilloscope in Vivado. This this signal is used directly from Vivado. Also, we can check in here at channel 7, which are the PWM pulses. In this case, we are in closed loop, but if we change to open loop and upgrade it, you see that now they are thinner. Sorry, I moved the zoom. However, if I change the data cycle to a higher value, for example, 80%, you will see that the pulses are now much thicker. I'm going to choose to close loop again and update that. And I'm going to select in here. I'm closing the time of the oscilloscope and, sorry, a bit higher. I'm going to check exactly how good or how bad is our control stage. So for that, we have in here a pusher, which is this blue and red item in here. So by clicking it, we create a 20% load step. In this case, you can see in the current in here, in the blue line, the load step we have created. This load step is reflected into a current step. And if we look at the voltages, it has had no effect on it. So our control is working quite good. We can even increment the value and make it again. You see that still very, very small and almost negligible effect. We can even change channel 1, which is the yellow one, into AC to see some kind of transient. And I think it was around here. Still at 200 millivolts, quite negligible. If we increase that and perform again, you see that the voltage step that we have created with a 20% load step is almost zero. It is one division is 15 millivolts, and we are around 1/3 of a division, so around 15 or 20 millivolts. So the control we have created is quite stable and is a quite good control, even that the switching frequency is at 300 kilohertz. For those of us which are interested in this platform, We have tested this board to a switching frequency of around 1 megahertz, so you can try with that. I go back then to the slices. We have covered how to measure that and the test point. We have skipped seeing in here the PWM, etc., because we have it available in the embedded oscilloscope. So what we have seen today? We have seen how to use the SmartRCP platform we provide, how it can be used to control, in this case, a buck converter, but it can be used to control whatever converter or system you have, as the hardware specs of this SmartRCP system is awesome. It can be used to accelerate time to market of power electronic converter, and more specifically the development of power electronic control in the range from several kilowatts, or in this case it is even lower, to up to megawatts converter. Also, SmartRCP provides a perfect balance between digital processing power and hardware interconnectivity. As you have seen with the example we have provided today, we are using about 2 or 3% of the internal resources of the system on chip embedded in SmartRCP, and just a really tiny part of the hardware provided by the SmartRCP. So there is almost no limitation with this platform. So what we provide, or what SmartRCP product includes? It includes the hardware platform, which is the white one. Also the template that we provide with the driver, which are the one we see in Vivado. Several Vivado project already done with a test mode, and also we provide the example we have performed today. We provide an embedded oscilloscope. We provide the buck converter demo board and the user manual. With this SmartRCP system, user has full access to all internal hardware. We provide several templates, but user can modify them, create his own template, and expand all the capabilities. So, would you dare to try that? Okay, so thank you very much to all of you. This is the end of the webinar, and now I provide you some contact information. You are invited to write to us into sales, or also the support emails. You can check more information in our website and also in LinkedIn. And of course, stay tuned, because we will be creating more material and more RCP tutorials. So that is all. Thank you very much.